Slide 1. Thick-walled cylinders. In this lecture, we will study thick-walled cylinders. These are cylinders with relatively thick walls that are subjected to internal or external pressure. Because the wall is thick, the stress inside the material does not remain constant. Understanding thick-walled cylinders is important for designing safe, high-pressure components in engineering. Slide to comparison of stress analysis and pressure. Pressure vessels can be analyzed using different methods depending on their wall thickness. If the wall is thin, we use simple equations. If the wall is thick, we must use more advanced theory. Choosing the correct stress analysis method is essential to ensure accurate and safe design. Slide 3. Definition of cylinders. Cylinders subjected to pressure include pipes, boilers, pressure vessels, and gun barrels. These cylinders may experience internal pressure, external pressure, or both. The classification into thin-walled or thick-walled cylinders depends on the ratio of wall thickness to inner radius, not just the physical size of the cylinder. Slide 4. Thin-walled cylinder. A thin-walled cylinder is defined when the wall thickness is small compared to the inner radius. Typically, this happens when the thickness divided by the inner radius is less than or equal to 1/10. In this case, stress across the thickness is assumed to be uniform, and radial stress is neglected because it is very small compared to hoop stress. Slide 5. Thick-walled cylinder. Thick-walled cylinder exists when the wall thickness is greater than 1/10 of the inner radius. In this situation, the wall is relatively thick, and stress varies significantly across the thickness. Radial stress becomes important and must be included in the analysis. Thin cylinder assumptions are no longer valid. Slide 6. Stress components in a pressurized cylinder. 3 main stresses are present. Hoop stress acts around the circumference of the cylinder and tends to split it lengthwise. Longitudinal stress acts along the axis of the cylinder. Radial stress acts through the thickness of the wall, either inward or outward. Slide 7. Stress distribution in thin cylinders. Stress is assumed to be uniformly distributed across the wall thickness. This means the stress at the inner surface is approximately the same as the stress at the outer surface. This assumption simplifies calculations and is acceptable only for thin-walled pressure vessels. Slide 8. Stress distribution in thick cylinders. Stress distribution is not uniform. Hoop stress is highest at the inner surface, where pressure is applied and gradually decreases toward the outer surface. Radial stress varies from maximum compressive stress at the inner surface to zero or external pressure at the outer surface. Slide 9. Equations of stress in thin cylinders for thin cylinders. Hoop stress is calculated using internal pressure, radius, and wall thickness. Longitudinal stress is half the hoop stress. Radial stress is neglected because hoop stress is the largest. It usually governs failure in thin-walled pressure vessels. Slide 10. Stress in thick cylinders using Lahm's theory for thick cylinders. Stress varies with radius and must be analyzed using Lahm's theory. Radial stress is expressed as a constant minus another constant divided by radius squared. Hoop stress is expressed as a constant plus that same term. These constants are determined using boundary conditions. Slide 11. Key points of Lahm's theory in thick cylinders. Radial stress is not zero and must be considered. Hoop stress is maximum at the inner surface and decreases toward the outer surface. Overall, stress distribution across the wall thickness is non-uniform, which makes thick cylinder analysis more complex than thin cylinder analysis. Slide 12. Summary of thin and thick cylinders. Thin cylinders have uniform stress distribution and use simple formulas. Thick cylinders have non-uniform stress distribution and require Lahm's equations. Thin cylinders are used for low to medium pressure applications, while thick cylinders are used in high pressure applications such as hydraulic cylinders and gun barrels. Slide 13. Determination of constants A and B. To apply Lahm's equations, we must determine two constants called A, B, and B. This is done by applying boundary conditions at the inner and outer surfaces of the cylinder. First, we identify the inner and outer radii. Slide 14. Boundary conditions. at the inner surface. Radial stress is equal to the internal pressure and is compressive. At the outer surface, radial stress is equal to the external pressure. Pressure values are taken as negative because they cause compressive stress in the material. Slide 15. Solving for constants. A and B, the boundary conditions, are substituted into Lam's equations to form two equations. These equations are solved simultaneously to determine the values of constants A and B once A and B are known. Stresses can be calculated at any point within the cylinder wall. Slide 16, final step finally. The values of constants A and B are substituted back into Lam's equations. This allows us to calculate radial and hoop stresses at any radius between the inner and outer surfaces of the thick cylinder.